Why, hello there. Welcome to our second topic on SQL, Advanced SQL. Now, I know the notes for today say Intermediate SQL, but you should believe the hype. This is advanced, cool stuff. The first thing that I want to talk about is the ability for SQL to compute aggregates. So far, we've just seen SQL used to select certain attributes or to filter using a where clause, things like that, to join. But we can actually have SQL aggregate the values across some number of tuples, which, as we'll see, is going to be useful for many different types of queries. So there are 5 aggregates, kind of aggregate functions that we can use in SQL that I wanted to mention. We have the ability to average the values of some attribute, find the minimum or the maximum, to sum up the values of an aggregate, as well as simply count how many tuples are returned by a particular query. And we use these in the select part of the query. So for example, select count of star from student would simply return the total number of tuples in the student table. So I actually want to switch over to the terminal to show you how these sorts of queries are actually working in SQL. So magical transition now. And I have both Postgres and SQLite up here. There are a few differences between them that, well, one in particular that I wanted to highlight. Mostly I'll do it in Postgres because the output's formatted a little nicer. As a preface, something that I didn't get to mention in lab is that both Postgres and SQLite, which you're using for homework 1, have some commands kind of that don't relate to querying the data that aren't SQL, but are for finding information out about the database. So in Postgres /d tells us all the tables, the relations that are present, and I have loaded up the kind of small university database that has been used for the practice problems and it is used in the textbook as a running example. And I can also say d student to get the information about a particular table. I get a lot of information here, the column, the attribute names, their type, whether they can be null, indexes, constraints, such as primary key and foreign keys, that sort of thing. SQLite has these same sort of commands. Dot tables shows you just the names of all the tables, and I can say dot schema with a table to get information about that particular table. So again, student IC has these four attributes and their types. And one nice thing that we can do with a small database like this is just select star from student to just see all the tuples in that relation. Now, if there were thousands and thousands of students in this table, select star from student would give us way too many. So to preview a kind of advanced SQL that I will talk about a little later on in this lesson, we can actually tell a query to limit the number of tuples that it's going to show us with a limit clause. So this comes at the end of the query, and so we can say select all attributes from student, but limited to just 10 tuples that get returned. So in homework 1, if you are like, well, what are the tuples in this table, the area or the artist or the release table look like? You can run a query like this to select kind of all the attributes from a particular table and just limit the number of results so you don't get a huge amount of text dumped out. All right, let's clear these up. Back to aggregates, as I was saying, we can do select count of star, kind of selecting the whole tuple from student to see how many tuples are in there. There are 13, and it actually doesn't matter what we put inside this count, because it's simply aggregating over all the tuples are returned. It doesn't matter whether it's one star for all the attributes, or one attribute, or even something silly like 1. It's just going to kind of count for each tuple in the output, and so what goes inside the count parentheses doesn't matter. Can we even leave it empty? No, you do have to put something there, even though it doesn't, in this case, matter what it is. We can kind of, to do a more interesting query, we could say, how many students are there who are from the computer science department? So we'd use where to say the department name equals comp sci, and comp sci needs a period, so there are 4 students in the computer science department in this table. So that's a little more interesting. Something else that count can do is it can do some sort of filtering as part of it. And specifically what I mean is to say I want to count the distinct department names in this student table. So I want to know how many different departments are represented in this student table. And so department name is an attribute of that table, and so if I just counted department name, it would count 1 for every tuple in the output, and we'd get 13 like we saw before. But when I say distinct, it's going to eliminate duplicates before it does the count, and so we see that there are 7 different department names in this table, and if we get rid of the aggregate, we will be able to see just the 7 distinct department names. All right, so other things about aggregates, we can actually have multiple aggregates in the same select. So we might do something like select the average of the total credits. This is something else that's in the student table, and count the number of IDs. And we'll do from student where our department name equals comp sci. And so the average of the total credits, 65.5, and this is an average of 4 tuples. So the total credit values for 4 tuples will average together. So we have kind of 2 aggregates as part of the same query. Now we might think to say, well, can we include non-aggregates in this query? So if we're getting the average of the total credits instead of counting the ID, what if I wanted the name of the student, like or the department name? What if I wanted the name of the student? Postgres is actually going to give me an error in this case, because I have an attribute name that is not part of this aggregation. So I'm averaging over the output tuples to average total credits, and if I'm averaging over 4 tuples, as we saw here, which of those 4 names should appear with the average? It's not clear, and Postgres says this student name must appear in a group by clause, which I'll get to in a moment, but Postgres doesn't let us do this. This is where SQLite makes a different decision. If in SQLite I take this same query and paste it in here, SQLite says, sure, I'll run that query, I'll compute the average, and just choose any of the names from the tuples that were averaged. Which one is just going to depend on kind of the order in which they are processed by the query. But SQLite does not warn us that what we're doing doesn't really make sense. It just picks a name and slaps it into the result. So what if we wanted to do this sort of query in a for real, where we want the average, but we want kind of some attribute of the table to appear alongside it that's not an aggregate. What we do there is use this group by clause. So go back to the board for a minute, and we know so far, we've seen so far that our SQL queries, we have a select clause, and then a, like, what is the data we want, then a from, where is the data coming from, then a where clause, which lets us filter the data, right? I understand, like, where department name equals comp sci, we're filtering out just the tuples from computer science, and it's after these three that we get to group by. Note there is a space between group and by. It's not one word. And group by, we provide an attribute here, and what one or more attributes, in fact, and what this group by will do is take the output tuples from the query and kind of group them together according to whatever attribute this is. So all the tuples that have the same value for the attribute we're grouping by will be grouped together, and then we can aggregate, have our aggregates over each group. So to show you concretely what I mean, let's return to Postgres and say what we can do is we want to select the average total credits, and we want to break this down by department. So instead of saying where department equals computer science, I'm going to say show me the average total credits among the students for each department. And so I don't want to filter them at all, so I won't have this where clause, but I can say group by department name. Actually move this over, there we go. Select the average total credits and department name from student and group them by department name. And so now for each of our 7 departments, it will display the average for just the tuples that have that matching department name. So average total credits among finance majors, history majors, physics majors, and so on in this table. And so this group by will let us do a lot of kind of sophisticated queries where we're taking our data and partitioning it and grouping it in different ways. We might say we might want to filter by the aggregate that we're outputting. And so we might think to say that what we want is we want to, from students, where it's the case that the average total credit is greater than 80. But unfortunately, this is not what we can do with aggregates. We can't use aggregates like average in our where clause, because, as I mentioned, the grouping is taking place after the kind of any joining and filtering from select and where. But as I hinted in the previous SQL topic, what we can do is have a separate clause having that comes after the group by, and in having we can have our predicate, just like we have a predicate in where. So we can filter in the where clause by some individual attribute value of our tuples, and in our having clause we can have a predicate on an aggregate. And so this having is what we would use to filter according to some aggregate that's coming out of the grouping. So to kind of close the loop on doing this in Postgres, instead of saying where the average total credits is greater than 80, we can say having average total cred greater than 80. And then we get out just the two kind of groups and their averages that meet this having criteria. So we now have kind of we've gone from 3 to 5 kind of major clauses, and as we've seen, we don't have to. We can kind of use them in different combinations. Though having only makes sense if we have a group by, since it applies to group things. All right, so that's aggregates. Move on to another kind of more advanced thing about SQL. So beyond aggregates, and let's talk about string operations. So all we've seen with strings so far is like a where clause that says department name equals comp sci, or basically checking for strict equality on strings. And so it's actually the case that we can use the percent character will match any string, and so this is like a wildcard, like a star, if you've seen regular expressions or something like that. But percent will match any string, and an underscore will match any one character, and so we can. And we use this in combination with the like keyword in order to, if we have a string that includes one of these kind of wildcard characters, we can use like to filter by strings that kind of match the pattern that we've described. So, for example, if in our where clause we say we wanted to filter by department names that are engineering. So we, with our kind of previous knowledge, we would have had to say like department name equals electrical engineering, or department name equals mechanical engineering, or department name equals so on and so forth. But instead of this equals, we can say department name like, and then we want to say percent space engineering. If, say, we know that all engineering departments will have the ENG period at the end, but we say anything percent, remember, is going to match any string. So this will filter all tuples to where the department name matches the pattern of any string, followed by a space, followed by eng and a period. And so this this can be very useful for doing queries involving strings. Now, there's some differences in how strings are handled in different database systems. So the kind of two properties that vary are the case sensitivity and quotes. So in Postgres, Postgres, we have sensitive, and it uses single quotes for strings. MySQL, Postgres and MySQL are two open source, kind of free open source database systems. MySQL is the weird one. It's case insensitive. So it does not differentiate strings by lower and upper case, a bit weird, and it allows single or double quotes to be used with strings. What we're using for homework 1, SQLite, it is case sensitive. And it, like MySQL, allows single or double quotes. And then they kind of commercial, a lot of the commercial systems are like Postgres. So IBM's DB2 and Oracle, both of these are sensitive, but both only allow single quotes. So kind of the assuming it's case sensitive and single quotes is kind of the most common thing, but not everywhere. And it gets kind of more fun that all different database management systems define their own sort of string functions that you can use. So there is a function like substring spelled out that's available in SQL Server, which is from Microsoft, and MySQL. But SQLite doesn't have substring, it has substr. It only has, it calls the function substr instead of substring. And so these sort of differences where each database management system is sort of doing its own thing a little bit is something you definitely need to be aware of. And I'll link a fun demo from Andy Pavlo in the description of this video, where he shows how crazy it can get, even when trying to answer a simple question like how many days has it been since the start of the year. This turns out to require pretty different queries in different database systems. All right, so next advanced thing is being able to redirect the output of a query to some other place. So let's get rid of our string nonsense here. And we can say, so we've seen that the kind of default thing is for the result of a query to be printed to the terminal, or otherwise displayed to the user. But we can actually tell SQL to put the results of a query into a new table or insert the results of a query into an existing table. And for this, we have a kind of new clause. If we want to store in a new table, so store the output in a new table, what we would do is between select and from, we would say into our new table. So this would say, so we'd have like select our ID into a new table, and then from, and so on. And so whatever our output, our query return would be, put into this new table by this query. If we had this into and some table name between our select and from, and we can also to insert into an existing table, we would say insert into whatever table it is, and then after this, in parentheses, are the query whose results we want to insert into a new table. So with our normal select from etc. inside parentheses after this insert into table. So we can select into a new table or insert into table the results of some query. Database management systems will typically also have ways to output the results of a query to a file, but that's not going to be SQL based. That's going to be kind of commands that vary between database systems. All right, so next on our advanced SQL agenda is controlling the output of our queries in different ways, and here we're going to have a couple more clauses added to our growing list of SQL capabilities. And so first we're going to be able to sort the output of our queries. You may remember that our tables are unordered sets. There's no order opposed on the tuples. The database is kind of free to store them however it likes. And our queries, I said, used bag semantics, meaning that they allowed duplicates, but they were also unordered. But we can impose order upon chaos. We can tell SQL to sort our tuples according to some property, and we do this by the order by clause, which going to come kind of at the end of all these, and again we can give it one or more attributes that it's going to use to sort the output of the query, and we can optionally say ascending or descending, ASC or DESC, after our attributes, and in fact after each attribute that you list separated by commas, to just tell it whether it's sorting in ascending or descending order, ascending being the default. The other way, which I already mentioned, that we can use to control our output is to tell it to only give us so many tuples back, and that's the limit clause, which we just limit it to some number of tuples that we want back. And we can even be a bit trickier because so unless we are sorting it, the tuples that are returned when we limit the output we're at the mercy of kind of whatever order the database has them in the results. We're just going to get the first number of them by this limit. But if we are ordering them, then we will get kind of a predictable tuples back because we're going to get the first some number of the sorted ones. And we can also tell it to offset by some number. And this says, all right, and this has to go with limit. And this is, all right, we're going to say limit it to 10 tuples, but not the first 10. Go forward, I don't know, 50, and then give me the 10 tuples there. So you can kind of use these to look through, say, chunks of ranges of tuples within the output if you want to do something like that. So let's see examples of this in our Postgres database. So clear things up here, and if we wanted to get the names of students ordered by the credits, their total credits, so we could say select name total cred from student order by total cred. and this gives us all the 13 names with the total credits sorted in the default ascending order. If we wanted the most at the top, we could tell it order by total credits descending, which gives us in the other order. Now we can, I said, give it multiple attributes to sort by, and this can give us sort of nicely formatted output. So we could say name, total credits, and let's add in department name so that we can see that I can order by department name, and I can order by with total credits as a sort of second, and I'll make that descending again. So it's order by department name, comma, total credit. So it's first going to sort them on department name, and then within that, with kind of the tiebreaker within that, will be total credits. And so what we'll see is that we've sorted by department name alphabetically. So all the students in computer science are kind of adjacent in the output because it's sorting by department name, but then to order the tuples within this sorted group of computer science, it's sorting by total credits descending. And so this is a way to sort of organize our output in a sort of nice and easy to see fashion. Okay. All right. So let's get a little crazy. We've seen that our SQL queries can get kind of quite complex. They can have all sorts of different parts to them. But not only that, our SQL queries can actually have other SQL queries inside them. So we can actually put these in many different places. And so you can simply have another SQL query in parentheses appear in the select, in the from, in the where, and it will kind of run this nested query and then use those results in that spot. So for example, if we wanted to find the instructor earning the max salary, one way that we could do that is to say we want to select the name salary from instructor where salary equals, and then in the where clause we can, with parentheses, just put another query that gives us back the maximum salary, which is how we want to filter the results from the instructor. So we can say where salary equals, and then select max salary from instructor. And so we have this nested query inside our where clause that selects the max salary from instructor, and that's what we're filtering on for salary equals. There's these nested queries. They can be used like this to kind of compute some value that we want to use as part of a predicate in our where. They can be used as to kind of compute some temporary new table. So in your kind of list of tables that you're selecting from, you could include a nested query there to compute some results that you want to join or select from. And you could also, though I expect this to be less common, have a nested query appear in the select so that one of the things in your output is the output of some nested query. We can also, there are some additional keywords that we can use with nested queries in our where clause. So in particular, we have four of them. We can say in all, any, or exists. And for these, it would be something like, I'm out of room on the board, so it will be something like what I will show on the screen here. So we can say something like, we want to find the names of all students who are taking the Intro CS course in our database, which is CS 101 in this case. And so we could say select the name from student, where the ID of the student is in this nested query where we're going to select the IDs from our takes table, which has a tuple for each student enrolled in a particular course, from takes, where course ID equals CS 101. And so we have this in, which says we want to filter tuples from student where the ID of that tuple is in the results returned by this nested query. And so when I run this, I get the six students who, if I go ahead and look at the takes table, we can see that we're getting the folks that had taken CS 101 kind of at any point in our table. And so these nested queries, very powerful. And you might say, well, is this nested query in this case any different from joining student and takes and approaching, so finding the students that have taken CS 101 that way? The answer is no. That these are kind of two different ways to kind of write the same kind of query, get the same results, and so. And in some cases, the database system may actually underneath be kind of doing the same operations, but not necessarily. And if so, in kind of this is where kind of database administration can go quite deep. Is like, okay, we have these different ways of writing these queries. You would need to understand the way that the particular database system that you're using is going to execute these different queries if you were trying to decide, all right, which one of these is a more efficient way of doing it. And this is something that is likely to differ from database system to database system in that way. But the thing that I want you to take away from it is the flexibility of these nested queries and the way to and the way we can use them kind of in our where or from to write kind of more complex or more expressive queries. Okay, we're most of the way through. Two cool advanced things about SQL remain. So the first is what's called a window function. So let me go back to our board view. All right, so a window function is something that we can put into our select statement. So let me get this out of here. And so a window function. And a window function is basically a way to compute an aggregate that preserves the original tuples and just kind of includes the aggregate as part of all the results. So what specifically I mean is that if we have some set of tuples, the aggregates that we saw at the beginning take all of these and kind of reduce them to a single result. summing them up, say. Our window function is going to have our 3 tuples and is going to still compute our aggregate, but instead of the single aggregate as the only output, it will include the result of that aggregate as part of all the original tuples in the output. So this would be a way, for example, to compute the sum of total credits in our student table, but instead of just getting that sum as part of all the student tuples that we had originally. And so the syntax for this is that it appears in the select, but we have our aggregate sum, and then we have the keyword over, and then there's potentially things that can go in here that will have similar effect on our output as our group by and order by, but this is we have our aggregate over, and then potentially some things to control the output is how we would do a window function. So let me show this by example, because I think that's a nice, clear a way to appreciate what's actually going on here. So we could say select the sum of total credits, and for now we won't put anything in the over, and we'll just get everything else along with it from student. And so what we have in this sum column on the left is the sum of all our total credits, but instead of if we just had select total credit from student, we would just get 854 instead of having 854 as part of each tuple. So this would be a way to kind of compute some aggregate and have it carry through in the results that maybe is being passed off to some further computation. So the things that can go inside our kind of over, as I said, are analogous to our group by and order by. So to put them up on the board, are what we can have in here. We can have partition by, which, like our group by, is going to have some attribute, and is going to kind of cluster our tuples or group our tuples by that attribute for the purposes of our aggregate. And we can also have an order by inside this parentheses, which will then order order our output just like our order by here. So if we were to use these things in our SQL query, let's say that we wanted to sum up the total credits not across all students, but we wanted to see the sum by department. So we could say partition by our department name, and now what we're seeing is the sum that is being added to each tuple here is the sum of the total credits within a particular partition by department name. So you can see all the 4 students from computer science all have the same sum 246, which is the sum of just the total credits of computer science. Biology, the sum is just the 1 student's credits from biology. Physics, it's the 3 students from physics sum who appear in the sum here. So we're getting this sum, but we've kind of done a grouping of this aggregate not by group by, but as part of this window function. And I said that we could also have an order by as part of this window function. And so we could also order by total credits. And so now within each of the partitions by department name in our output, those tuples are ordered by the total credit attribute. And I have just learned by doing this example that when you combine the partition by and the order by, you can actually get a cumulative sum. So the first tuple in computer science is just that student's credits, and then each sum after that is a cumulative sum. So that's pretty neat. Being able to get a cumulative sum with a fairly simple query. There's one sort of special window function that kind of isn't one of our normal aggregates, and that's the row number and rank window functions. And so we can say select row number over optionally a partition or an order by from student. And this just gives us the row number. This will be more interesting if I include the rest of the tuples. So here we're just getting the row number, right? It's just numbering the rows, which is not that exciting. But if we were to order by our total credits, now the row number is applying to the rows in the way they appear, and so we're actually seeing that the kind of the last one in the sorted order is 13, the first one is 1, and we can in fact add our partition by department name back into this. And what we're actually seeing here is that within each partition now we're getting the ordered row number. So the the 4 computer science students are ordered by total credits, and then there's a row number assigned for each one in that partition, so that the student with the most credits is row 4, and the student with the fewest is row 1. Last advanced SQL thing for you is what are called common table expressions. So common table expressions, or CTEs, are a way to kind of have a query. It's a similar idea to nested query, except that you are kind of writing a full query that will be available as a sort of temporary table for use in another query. And so how this works is that you say with query name, you're going to give your query some name, it's whatever you want, as parenthesis, and then you're going to have a full SQL query in here. And then after you close the parentheses, you can then do another query, select whatever it is, and you can use this query that you've named as kind of anywhere within this main query. So we could select from query name other table and say join some other table with the results of this query name. So this, and we can actually chain these CTEs together. So you can say like with query name as this, and then a comma to chain these together. you would with query name as such and such, and then other query as, and then another query, and then you could then at the bottom write your main query, and you could use both query name and other query as if they were tables in your main query. And so, as an example, sort of a query that would be quite difficult to write without using one of these CTEs, I want to show you an example. And so the query that I want to write is to find the instructor in each department who has the highest salary in that department. So I could say something like with max salary as, and then inside here I want to select max salary. And I'm actually going to rename this max field so I can refer to it later on. I'm going to give it a nice name that I can refer to that attribute. So max salary as MS, department name, from instructor, group by department name. So I'm doing my kind of common table expression has this is using a aggregate and group by to get the max salary of the instructors in each department. And so now I've finished with my common table expression. I can write my main query, which is going to be to select the instructor name and the department name from instructor and my max salary table, where, and then I'm going to want to join this instructor department name is the same as the max salary department name. So I want to make sure the departments match up. And I want it to be the case that the instructor salary is the salary that I found as the maximum for that department. And I have made, it is warning me that when I said select department name, there's a department name in both instructor and max salary. So it says there, this is ambiguous. I don't know which one you mean. So now I have I have gotten the instructor's name and the department name for the kind of the highest paid instructor in each of the departments using one of these common table expressions. I think you could also do this with a window function by ranking them, but it is a good example of kind of where having this sort of pre-computed temporary table of max salaries, which doesn't exist in our database, and we might not want to create a whole new table just for this, but we can, with a common table expression, create this kind of temporary table that is bound to just this query, and it gets kind of thrown out once we're done. I will mention that you can also make these common table expressions recursive. It's not clear to me when, this seems very a special case that making these recursive is quite unwieldy and seems of limited utility, but you can do it. SQL indeed is very advanced. All right, I hope you feel the advanced SQL, the SQL power flowing through you, and I look forward to your questions, and good luck on homework 1. All right, Black Void, where are you? I'm ready for you. It's above me, isn't it?